One. Okay, whenever you're ready, go ahead and give it a start.
Or one of the cats approach. I think I'm good. Let's see. Let's see. I'm not on the right slide. So you can't see my slide
So
at all, right?
I can't see your slide at all.
Okay.
All right, so go ahead and start.
Okay. Hello. Thank you for attending the Amazon Web Services Innovate Online Conference. My name is Sean Wilkinson, and I'm a machine learning specialist solutions architect. Specifically, I'm a machine learning specialist solutions architect who works exclusively with startup customers in North America. And like when I speak to startup customers, there's a consistent theme and consistent questions. They're always asking how can they build models faster and for less money. Startup customers in particular are looking to extend the runway by reducing costs while also getting their models to production faster. My talk today is called How to Accelerate Your Models to Production with Amazon SageMaker. It includes advice and tips I've seen startup customers implement successfully in AWS. These tips all involve lowering costs and iterating faster. So first, we'll do a brief overview of Amazon SageMaker, AWS's managed machine learning platform. In general, this discussion is going to focus on SageMaker, but the ideas and concepts can be generalized to your data science work anywhere. In particular, I will focus on deep learning, speaking to a specific computer vision example, which will lend context to some of the suggestions I give. After the overview of SageMaker, we'll cover machine learning training, focusing specifically how to reduce model development time and save costs on training infrastructure. Finally, we will conclude with advice related to model inference. All right, let's get started. As I mentioned, we'll start off with a brief overview of SageMaker, which will lend context to the rest of the presentation. Amazon SageMaker is AWS's managed machine learning service. It accelerates data scientists' work by automating common machine learning tasks. It is a growing suite of features ranging from data labeling to model monitoring. However, the vast majority of the features build off three fundamental components. The first is an integrated development environment for data scientists. It consists of a secure, collaborative, and managed Jupyter environment for daily work. Second is a managed training platform, which provides fully managed infrastructure. It includes experiment tracking, model lineage, and hyperparameter tuning. And then lastly, we have a managed hosting service. It can be used to quickly set up and serve your model at scale. You're encouraged to use all these features a la carte if needed. You don't need to use the whole suite. You could just use one or two or all of them, depending on your use case. It's important to note that they're not tightly integrated. For today's discussion, we're going to focus primarily on 2 and 3. We're not going to discuss the development environment. So, what does a SageMaker training job do? Well, after you package your training algorithm and code within a Docker container, when you call the SageMaker training API, SageMaker spins up ephemeral managed instances running your container. SageMaker then downloads your training code to the container and initiates the training code, while emitting logs and metrics to external storage so you can monitor the progress. At the conclusion of your training code, SageMaker saves the model artifacts, records, and logs, hyperparameters, and model metrics durably to storage before shutting down any compute resources. Some aspects to note here is that it minimizes the time compute resources are allocated, reducing your overall costs, and then also that the model lineage is tracked. So input data sources, model artifacts, parameters, those are all tracked. That's critical for model reproducibility. And of course, you're welcome to bring your own training code or algorithm as you see fit, which we'll go into more detail on the next slide. With respect to the container itself, there are three possible layers of abstraction. At the highest layer of abstraction, you have the SageMaker built-in algorithms. These are first-party algorithms, and in this case, the algorithm, container, and infrastructure are all provided by SageMaker for you. All you need to do is specify the training data set. This can be a great choice if you're using a popular algorithm that's open source or model, for example, like ResNet or PCA. These algorithms are built to scale well, so you can be confident that it'll work with large data sets. In the middle, we have what we call script mode. In this case, you leverage the SageMaker built-in containers. These containers are pre-populated with open source libraries that you may use already, like scikit-learn, TensorFlow, or PyTorch. The containers also already conform to the SageMaker interface, allowing you to easily leverage additional SageMaker features, as we'll see later on in the presentation. In this case, all you have to do is bring your own data and training code in the form of a Python script, and SageMaker provides the rest. And then lastly, at the lowest layer of abstraction, for those who like to do it themselves, you're also welcome to package your own container and bring your own code as you see fit and just leverage the SageMaker managed infrastructure on its own. So that completes the brief overview of SageMaker. Now we'll dive into the startup specific content related to cost optimization and development acceleration. So to lend context to the conversation, I'm going to speak to a computer vision model I trained using the PyTorch container last week. This will provide concrete use case as well as example numbers to describe some of the features that we're going to talk about today. So by using the built-in PyTorch container, I still need to provide my own training code, which includes the training loop, where it iterates through gradient descent steps to optimize the performance of my model. While I'm writing and troubleshooting the training code itself, which consists of a Python script, I do it locally in my local dev environment on my laptop. Troubleshooting locally is convenient, it's fast, and oftentimes I'll catch simple errors before having to launch a discrete training job. In addition, I don't pollute my logs and experiments with failed training runs, which can be a little bit embarrassing. But if I'm just testing and troubleshooting my code locally, how do I know that the code will run correctly once it's in SageMaker? Well, there's an easy way to do that. You can leverage the SageMaker local mode. So in local mode with the SDK, it launches and runs the Docker container that will be running in SageMaker, but runs it instead in your local development environment, while optionally writing the results to S3, as we see in the slide here. This allows you to conveniently test your code from your development environment before launching any long-range training jobs. Doing this confirms that your code runs and interfaces with SageMaker successfully before you even get started. So in my case, with this sample computer vision model, I make sure to test it locally and make sure it's successfully running and making a few steps like within the training loop before progressing further. To show you how to implement this, I have a screenshot from my example notebook. It's just one parameter change. So instead, when I launch my training job, I'll specify the instance type to be local, as opposed to specifying an AWS EC2 instance. So with that one parameter change, it will spin up a local container as opposed to an external container in the cloud. You will need to have some dependencies installed on your local environment, such as Docker, for this to work correctly. So now that my training code is running locally, it's time to start using more powerful compute resources, maybe ones that have a GPU. I suspect that a GPU will substantially reduce my training time because it is a computer vision model that has lots of computationally expensive computations. However, it will have an additional cost associated with it. These powerful instances tend to have a higher hourly cost. So as with all workloads on AWS, one of the top cost-saving techniques is actually to leverage spot instances. For those of you who haven't heard of spot instances, there are unused EC2 capacity in the AWS cloud that you can leverage for up to a 70% discount. The only catch is that your spot instance may be interrupted with a 2-minute warning if capacity is requested. Spot instances, in particular, are a natural fit for deep learning because deep learning training is very compute intensive, as I mentioned, often requiring multiple powerful machines that might have hardware accelerators like GPUs attached. Additionally, they're usually not time critical. Oftentimes, you can afford to wait a few extra hours or days to reduce overall costs. For example, you can run training jobs overnight or over the weekend as necessary. And then finally, they're also interruptible. All frameworks and libraries for machine learning allow you to save model state. So you can interrupt training, save the model state, and easily restart later when capacity is available from where you left off. So if you're interested in getting started with Spot instances, you may have to set up a job queue as well as the Spot fleet requests and manage timeouts and things like that. Alternatively, you can leverage Spot training in SageMaker just by changing one input parameter. So for this example, as you can see on the screen, I just set the use Spot instances parameter to true when I launch my training job. And after that, all my training jobs are run on unused EC2 capacity. There's also a parameter for model checkpoints. So we can use that to checkpoint our code periodically to external storage so that it can pick up from there in the unlikely event that it is interrupted. So for my computer vision model example that I ran last week, I saved 70% of my training costs just by changing that one instance parameter. This might be the best way to reduce compute costs associated with deep learning. So you may notice that at the top it says save as much as 90%, whereas on the screen it shows that I saved 70%. So what is the cause of that discrepancy? Well, Spot instances have market pricing, which means the available capacity and demand will affect the price you pay. In this case, my training job was not interrupted at all. However, SageMaker, in the unlikely event it is interrupted, SageMaker will gracefully interrupt your training job and restart it when capacity is available. So it handles all that queuing logic for you. Terrific. Now that my training code is running successfully, it's running on Spot infrastructure with the GPU, I want to make sure that the training code itself is as optimized as it possibly can, so it runs as fast as possible and uses the least amount of resources. To do that, I'd like to monitor and check all system resources, such as the GPU, GPU memory, CPU cores, and RAM, to ensure that they're all being fully utilized, and there's not some resources that are not being used at all. So some metrics, like CPU and GPU utilization, those are stored by default in external logs. But if you require further granularity, I recommend checking out SageMaker Debugger. SageMaker Debugger provides real-time feedback from your training jobs by storing tensors durably to S3, or external storage. You can define rules based off of these tensors to proactively detect errors, like overfitting, for example, and then intelligently stop jobs so they stop running and stop incurring costs. This allows you to avoid unnecessary costs associated with malformed jobs or malperforming jobs. It adds a layer of transparency to long-running deep learning jobs. And I think the best part is that if you're using the built-in SageMaker containers in script mode, like I mentioned earlier, you can actually leverage it with zero training code changes. It's already instrumented for you, which is pretty great. But what I find myself using the most actually within the debugger ecosystem is something called SageMaker Debugger Profiler. So SageMaker Debugger Profiler is a Boolean value you can set when you launch your training job. It will create a report that monitors system metrics that I mentioned earlier, such as RAM, CPU cores, GPU memory. It also produces an HTML report at the conclusion of your training job. So here's an example of a report generated by SageMaker Debugger Profiler. I know this is kind of zoomed out, but we'll dive deeper into some of the sections on the next slide. But the idea is that it monitors system metrics at an interval you specify. The default is 500 milliseconds. So it collects detailed metrics such as the CPU utilization for all the individual cores, GPU memory. So this can be very useful to detect underutilization of resources. But perhaps more importantly, on the right side of the screen, you'll notice that it provides prescriptive guidance on how we can improve our training code. So the arrow is pointing to a CPU bottleneck that it detected, but there's a variety of different recommendations it has on top of that. So let's dive deeper on the next slide into some of those recommendations. So this is some of the feedback that SageMaker Debugger Profiler gave me during my training run. So in the report, it said that my training code was actually spending the bulk of its time, as you see in this graph, outside the training and evaluation phases of the model itself. It flagged this as abnormal based on comparisons to other deep learning training jobs. And it recommended I optimize my code outside the training and evaluation phases. So based off this feedback, I went back and looked at my Python scripts, and I noticed that the majority of the code outside of those two phases was actually related to model checkpointing that I had implemented for the spot integration. I was making a checkpointing the model state every training loop, every epoch of my data set, and it turns out that this was actually quite frequent. And because the model itself was very large, this was incurring a large time penalty. So what I did was I changed the frequency or reduced the frequency of my model checkpointing, which further reduced my training time by 10%, which reduced the overall cost savings for future runs by 10% as well. So while this is some feedback it gave me, I think this is kind of the tip of the iceberg. There are many other many other feedback that it gave me as well, but this is just one that I was able to take action on immediately. All right, so our customers so for our model so far, it's running correctly, it's running on spot instances, and we've made some performance tuning to our script itself. For customers who are training large models, there is one final training optimization that they can make. So if you need to iterate on training runs faster, so you can distribute, you can try distributing training across multiple compute nodes and GPUs to reduce the overall training time. There are two different methods of distributed training. For one, there's model parallelism. This is for large models that are too big to fit into memory of a single GPU or CPU. This is the case for many state-of-the-art NLP models like GPT, which you probably have heard of. Secondly, there's data parallelism. This is for really large data sets. So you can partition data across multiple nodes or GPUs and share model updates between the two. Whether you are doing model parallelism or data parallelism, the SageMaker deep learning team has a library for you. They recently released distributed training libraries that make it easier to implement both of these methods. With a few lines of code, changes in your training code, you can achieve a near linear speedup. So it's not just that the libraries facilitate making this process easier, it also is a very efficient implementation. So this chart that you see on the screen here compares the SageMaker libraries for PyTorch Distributed Data Parallel, or DDP, which is PyTorch's open source implementation of distributed data parallelism. It compares that to the SageMaker libraries for distributed data parallelism. And you can see in the orange columns that SageMaker's libraries provide a significant speedup and achieve almost a 90% scaling efficiency when you add additional nodes. So if you are looking to reduce the training time of large machine learning models on large data sets, perhaps check out these distributed training libraries. At this point, we've covered multiple optimizations for machine learning training, and we covered the basics of SageMaker. Next, we'll take a similar look at machine learning model inference. So the first step in defining your inference architecture is deciding whether you'll do online or offline inference. Offline inference is serving your model with a web server to provide individual predictions with low latency, generally less than a second. On the other hand, offline inference generates predictions on a large batch of inputs all at once. It isn't expected to be real time, so you can run it daily or weekly as required. Some customers' use case dictate whether they do online or offline inference, and this may be the case for you. For example, customers generating predictions for ad serving systems generally have to generate predictions that have a strict sub-second latency requirement, so they are required to do online inference. However, if you do have a choice, offline inference is often much more cost-effective and easier to implement. There's a couple reasons for this. One, you can leverage big data tools like Spark to more efficiently transform your data in batch. Secondly, you can fully utilize the hardware available to you by using large batch sizes, as opposed to like a batch size of one prediction. This is particularly relevant if you're using a GPU for inference. And then lastly, with the power of the cloud, you can launch the compute resources only when you're generating predictions, then release them afterwards, which can save significant costs. For example, for my computer vision model, I was able to achieve 400 images per second inference with my computer vision model using G4 instances in AWS. Doing so, I was able to process all the images in my dataset in 5 to 6 minutes. So I only had to allocate that G4 instance for 5 to 6 minutes, as opposed to maintaining it for 24/7 to serve online requests. So you can see it ended up being a much more cost-effective solution than online inference. So in general, offline inference can be very computationally efficient and cost-effective, but in some cases, your hands may be tied and you may have to do online inference. But whether you're doing online or offline inference, SageMaker does have features to support quickly implementing them in the AWS ecosystem. You can use or extend the built-in SageMaker containers, which contain a web serving stack. So you can easily stand up a model serving endpoint. A SageMaker endpoint consists of a discrete URL backed by one or more managed servers running your model that you developed. So by creating an endpoint, you can quickly build an API to serve requests, like as you see in this diagram here. What we see here is actually the most common architecture pattern seen from our customers with SageMaker endpoints. It includes an Amazon API gateway at the front. API gateway is a fully managed service to allow you to create, publish, maintain, and monitor and secure APIs at scale. It provides a very polished front end for production APIs. It provides flexible authorization, throttling, API staging, everything you'll need to publish an API. In the middle there, we have AWS Lambda. This isn't necessarily required, but it is a cost-effective serverless compute offering that lets you run code without provisioning any servers. So it sits in the middle here and reformats or normalizes any incoming requests, maybe drops some of the data that's not needed. It can also reach out to external data stores like a feature store, for example, if that's necessary. This is a robust architecture that many AWS customers use at scale, and you can quickly stand it up by leveraging SageMaker endpoints. So in this architecture diagram that we see here, requests come from the user's application for predictions from our model from the left, flowing through API gateway, through Lambda, then to our SageMaker endpoint, which encompasses the right side of our screen. The models and the instances make a prediction and return a response that goes back through Lambda and back through API gateway. So Lambda, again, can do any post-processing as necessary before going back to API gateway. Now, if we're talking about cost optimization and hacks that I've seen machine learning startup customers implement, one that I've seen that's become even more and more popular is actually to host the model itself on Lambda directly. To be clear, this is outside the SageMaker ecosystem. But to do this, you would just need to package up your model artifacts that are created during SageMaker training and install your serving framework in the Lambda runtime environment. Lambda scales down to 0, so you don't pay for it if you're not being used, if there's no request, but it also scales up seamlessly in parallel with your business, which makes it exceptionally cost-effective and a natural fit for startup customers. So there's a couple things to keep in mind if you do try to leverage this approach. One is that you forego hardware accelerators like GPUs, for example, because that currently isn't supported in the Lambda ecosystem. Second, larger models and libraries will incur more significant cold starts. So a cold start is the delay from when a Lambda function is invoked to when the code execution actually starts. And the larger your model size and the larger libraries that you use, the longer the cold start will be. It's proportional. Finally, you won't be able to leverage some of the higher level machine learning features that are already implemented within SageMaker, such as model monitoring and model lineage. So you may have to implement these yourself. If you do go down this path, there's several performance optimizations that I recommend. The first is to consider using a model compiler. There's one in the SageMaker ecosystem called SageMaker Neo that you can leverage. The reason you'd want to do this is to reduce the model and serving framework size. So Lambda has strict limits on the package size. So this is one way to get around those, compile the model, make the artifacts smaller, make the runtime smaller, and make it more agile and depth. Secondly, leverage external storage if the model artifacts or libraries are too large for the Lambda limits. So for example, if your model size is too large for the Lambda limits, you could store it in external storage like S3 or EFS and load that dynamically when the Lambda environment starts out. And then finally, compile your code with flags such that they can leverage AVX2 instructions. So AVX2 instructions are CPU instructions that are designed and optimized for math, for arithmetic. So it's very good for vector operations, which is very common in machine learning, such as matrix multiply. So by compiling your model for this environment, for AVX2, you'll see a potential speed up in your operation code. So we've discussed online inference, but now let's go into offline inference. So for offline inference, SageMaker has a feature called batch transform, and this allows you to create ephemeral instances that spin up, read your data from your external data store, generate predictions, and then store it back in your external data store. And the idea behind SageMaker batch transforms is to really leverage the same code as your SageMaker endpoint. So you don't have to rewrite your inference code. You can use it for batch or for real online inference. However, actually one cost optimization technique I've seen multiple customers leverage is to use SageMaker training APIs for offline inference. Now, that's a little weird. Why would they end up doing that? Well, for two key reasons. One, offline inference is actually very similar to machine learning training if you think about it. You read data from your source data set, compute forward passes in your model, and then write the results to durable storage. There's a lot of similarities there. But most importantly is that by using SageMaker training, you can take advantage of the spot instance features that are available there that we discussed earlier. So you can get up to a 90% discount on these ephemeral batch transforms by leveraging the SageMaker training API. So that's one cost optimization you can get for offline inference. So the last topic I wanted to cover in the inference category was automated model deployments. So the most common topic of conversation in the past year I've had with startups was machine learning operations and choosing between the litany of orchestration tooling available for data scientists. In particular, data scientists are looking to productionize, monitor, and manage their ML models so they can own end-to-end model management, own the end-to-end model management lifecycle without depending on their engineering team or their DevOps team. Many customers in particular leverage open source orchestration tooling, such as Airflow. But whether you're using open source software or a SageMaker native tool, like SageMaker Pipelines, which you can see on the screen now, you want to empower your data science to iterate and deploy new models as fast as possible. The worst case scenario would be your data scientists develop models, and then your DevOps team actually needs to translate that code into another language or reformat it so it will work in your production system. That just doesn't add value and will slow down any experimentation by your data science team. So what SageMaker Pipelines does on the screen here is it breaks your training and deployment into discrete steps. So for example, as we see here, there's a step for pre-processing data, training, evaluating, and then deployment. That's a very common use case for SageMaker Pipelines. I actually think the SageMaker Pipelines example that you can find in our public GitHub repository does a terrific job of demonstrating an ideal handoff between data science and DevOps. The data science team can define their own pipeline using Python for model development, training, and evaluation. Once it meets their requirements, they can promote it to production in their own model registry. From there, the DevOps tooling can trigger based off the model registry. It can kick off their own DevOps pipeline. So the DevOps team can use their own DevOps tooling. They don't need to use the same tooling necessarily as the data science team. So they get the best of both worlds. So this example kind of demonstrates kind of the two views of model deployment that many customers have. They have the data science side and the DevOps side. So implementing a system like this, where each have their own pipelines and it's automated and automates the handoff between the two, that reduces friction and makes sure that the end model satisfies all the requirements of both of data science as well as DevOps. So we've covered a lot of different content today, mainly revolving around training and inference. But let's go to our takeaways to summarize what we've learned. The first is to troubleshoot your training code locally at first before scaling out to the cloud. The second is to leverage spot instances as much as you can during deep learning. And this applies across the AWS stack. Use spot instances and spot resources as much as you possibly can. And then finally, for training, leverage profiling tools to maximize resource utilization. You can use SageMaker Profile Debugger, but I know there are also excellent open source tools as well, such as TensorFlow Profiler. For inference, there are a few tips as well. One is to leverage pre-built serving frameworks and architectures whenever possible. There's a lot out there, so you don't need to reinvent the wheel there. And finally, for inference, definitely try to automate as much as the deployment pipeline as possible and minimize friction between engineering and data science by potentially implementing multiple pipelines that serve each of their interests. So that wraps up the content for my presentation today. If you're looking for a similar content to what you just heard, I encourage you to check out the following two sessions. They're very related to what I covered today, and they're created by some of my peers. The first is open source ML frameworks on Amazon SageMaker, and the second is scaling machine learning from 0 to millions of users. Of course, definitely check out all the content available at the Innovate On conference. There's a lot of great content out there. So if any of this caught your eye or you thought it was relevant to your current line of work, you can check out the following resources to dive deeper. The first is our public GitHub repository, which includes examples with SageMaker for all the features we discussed today and more. So that's a good way to get hands-on with code immediately. Secondly, if you're looking more for example SageMaker templates, guides, or pre-trained models that you can fine-tune, definitely follow the link at the bottom. That leads to SageMaker Jumpstart, which includes all that content I just mentioned. Lastly, I want to thank everyone for listening to my talk today. I genuinely appreciate it. I hope you got a lot out of it. Have a great rest of your day. Thank you.
Awesome. Okay, let me stop.